Okay, students, so now we'll study about the dot product. Dot product is also known as the scalar product. The reason it is known as scalar product because the final product you get is a scalar quantity. It's not a vector quantity. So that's why it's not known as a scalar product. So let's say we have two vectors, A vector and B vector. So if we want to get a dot product, so dot product means that you have to do A dot B. So this is given as AB cos theta, where you must have noticed that I'm not using any vector sign up there. So it means that I'm taking the magnitude of A and B. So since this has a magnitude, it has no a direction. So this is basically a scalar quantity. Cos theta is also a scalar quantity. So this as a whole is a scalar quantity. So that's why it's a scalar product. So always remember that dot product of two vectors is scalar, right? So this is given in this way. So this is the dot product. If you want to visualize this, then let's take two vectors, A vector, B vector, and the angle is theta, right? So you must know that by trigonometry, this region will be B cos theta. We just found out, right? So this is the B cos theta. This is the region we're talking about, right? So dot product is basically nothing but in a way that a projection of one vector over another. So how much one vector is projecting over another if they're at an angle theta uh, towards each other. So that's what dot product tells. But mostly this definition should do in most of the numericals. This is what which will get you through. So this was just the idea of it, and you should know the properties of dot product. So properties. So dot product is commutative in nature. That means A dot B is equal to B dot A, and also it's distributive in nature. Distributive means if you're writing something like this, you can break it down. So dot product allows that. So that's dot product. Okay, so now let's move on to another product which is known as the cross product, and cross product is vector in nature. So cross product is also known as vector product. So since this was known as scalar product, cross product is known as uh, vector product of two vectors. Okay, so cross, now when we're talking about dot, we put a dot there. So when we're talking about cross, we just simply put cross in here. So when you put a cross in here, the final value you get is if you take the magnitude of this, you get AB sine theta. So please note this is just the magnitude. Okay, I'm taking the magnitude of A cross B, then we're getting AB sine theta. So this is what vector product is about. This is a scalar quantity because we have taken the magnitude. If we don't take the magnitude, we get another directional, we get directional vector, something like this. So that's the scalar product. Sorry, that's the vector product, vector cross product. Okay, so this is clear. Let me visualize this one for you. So this one, we call it as the unit vector perpendicular to the plane. So what does this basically mean is that it's a trick. So A is, for example, on this side, and we're taking B on this side. So for cross product, what you have to do is that to find the direction of the final value, because this is a vector quantity, so it has to have a direction. Now this one tells us that it is an unit vector perpendicular to the plane. So plane is this page. This is the plane where both of the vectors are lying, right? So I want to find the direction of this cross product. So what you have to do is that you have to make your hand like this, right? I think my camera angle is too bad, but visualize it like this. So this is the A vector. So do it at your home. Draw A and B in this manner, and put your hand like this over A, right? And your thumb should point upwards, right? So we're doing A cross B, so you have to go from A to B. So when you have to go from A to the B, you have to do like this, right? You will do like this. So when you do like this, your thumb is pointing upwards, and point is thumbing upwards, and that your thumb gives the direction of A cross B. So your thumb is giving the direction of A cross B, so it's coming out of this plane. and that direction is perpendicular to both A and B and to this plane, and that's what it means. It's the unit vector perpendicular to the plane. Okay, so A cross B is perpendicular both A and B, and you can get this using this right hand thumb rule. You have to just take from A to B. If it was from B to A, then you have to take from B to A, then it will go downwards, right? It will go downwards then. So this was all about the vector cross product. So there are certain follow or properties that you should know, just like in vector scalar product there are properties of vector product. So properties, so A cross B is equal to minus B cross A, and it's quite obvious. I told you that in a vector, if it is minus, it basically talks about a direction, right? So when we're going from A cross B, we're going upwards. When you're going from B cross A, we're going downwards, like inside this page. So they are opposite in direction, so that's why they are equal in magnitude, but in direction is different, so that's why it's the minus sign. And it follows the distributive law just like it did in dot product. So you get A dot B cross C as A cross B plus A cross C, and third you get, and the third property is that it's not associative, so you can't go like this for vector product. So A cross B cross C may not be equal to A cross B cross C. That means that B cross C, what you will get, and then you'll do a cross product with A, may not be equal to a value of, when you're taking cross product of A and B first, then you're cross producting with C. So this property is not present, so it does not act like that. And also this basic thing which you might come across quite often is that if you're taking unit vectors I, J and K, so when you do cross product, so the unit vector will change. It will no longer remain the same unit vector. So remember this simple circle. Okay, so go it in a clockwise manner. So if you get I cross J, you will get K. J cross K, you will get I. So when I'm going from I to J, I cross J, I'm getting K. I'm going from J cross K, I'm getting I. But if I'm going in the opposite direction, let's say I'm going from I to K, so then this direction is against the direction of this arrow, right? So I cross K is minus J. So I'm coming to this again, but since the direction is opposite to the direction of this system, so we're getting a negative sign. So similarly you can get the rest, right? K cross J will be minus A, J cross I will be minus K. So that's the basic idea of how you change sign when you're cross producting using unit vectors. Also, there's one more thing that we need to talk about in dot product and scalar in vector product, is that when we're considering unit vectors, when you're doing dot product of unit vectors like I dot I or J dot J or K dot K, we need to understand that we're taking what will basically be, as per the definition, is that I dot I cap will be written as magnitude of I into magnitude of I and cos. So the angle between these two will be 0 because they are the same thing, x direction, so they are the same thing, so angle will be 0. So cos 0 is nothing but cos 0 is 1, so the magnitude is 1 because the magnitude of these are 1 only. So j dot j is 1, k dot k is 1, but when you're doing I dot j, you take magnitude of I, you take magnitude of j, but the angle now is 90 degree because I is x-axis, we studied before, and j is y-axis, so the angle is 90 degree in between them and cos 90 is 0. Similarly, I dot k is also 0 and j dot k is also 0. So this is the nature of unit vectors in dot product. And when it comes to vector cross product, so it's different. So I dot I and j cross j, sorry, and k cross k, they are all 0, because now if you remember the definition, if you go by the definition, then we'll have to take magnitude of I and sine theta. So sine is 0, sine 0 is 0, so we get 0. And as you can probably guess, that if I'm taking I cross j, then I'm getting the unit vector perpendicular to these two, because the definition of cross product is that we've taken that n cap vector, which was nothing but unit vector perpendicular to the plane, as I said. So if I and j are on the plane, then the z will be obviously out of this plane, right? So it's a three-dimensional thing. So that was the definition of vector product, and from that definition only we're getting it as k. And also we've studied that circular system, from where we're finding out what direction to get when. So this is the whole idea of vector cross product and scalar dot product.